Okay guys, it's Advanced Math Trig Honors, Mods 2, 3, and 4. It is now Wednesday, April 8th. We're going to wrap up our chapter on conic sections. For the past several days, we've done circles, ellipses, hyperbolas, and parabolas. Hopefully you're good at graphing a basic conic section that's written in standard form, or have the ability to put it into standard form if need be by completing the square. And we're going to kind of wrap the chapter up with just a couple of problems and show you one instance where these conic sections, these pictures, can even be utilized in calculus next year. So today, again, the date, top left corner of your paper, April 8th, 2020. The title is Systems of Conics. Yes, very similar to what you studied in the past called Systems of Equations. This is called Systems of Conics. And for right now, the first of our two problems, go ahead and write 4x squared plus 9y squared equals 36, comma, and then our other conic section is 9x squared minus 4y squared also equals 36. Obviously, they look very similar. The only difference, the major difference, I guess I should say, this has a plus in the middle. This has a minus. We know when we see a minus in the middle, we're automatically thinking, oh, that's a hyperbola. Now, this one over here, is that a circle or is that an ellipse? Well, because the 4 and the 9 are different coefficients, remember, that makes this an ellipse. Okay, so bottom line is, guys, look, I've got an ellipse and a hyperbola, and we're asking the question, put a big star next to the problem, where do they intersect? Where in the world would this ellipse and this hyperbola intersect each other? Now, to do this, of course, your first thought is, oh my gosh, if we want to know where do they intersect, we should probably draw them or graph them as quick as we can. They're pretty basic. And kind of get a feel for where and how many times they actually intersect. Well, if you notice, this one's equal to 36, this one's also equal to 36. We know darn well ellipses and hyperbolas have to be equal to 1 for you to graph them accurately. So in both cases, I'm going to divide both sides by 36. Making this one become x squared over what? 9, agreed, because it's 4 over 36, plus y squared over 4 equals 1. And then the hyperbola, when I divide that one by 36 on both sides, simplifying him into standard form, we've got x squared over 4 minus y squared over 9 equals 1. So if we're trying to figure out where do they intersect, let's draw a picture as neat as we can. Now, notice on both of them, we've got good old x squared and good old y squared, agreed? There's no x minus 1 or y plus 2 or x minus 3. So both of these have a center of 0, 0. So graphing my ellipse, we agree the center is 0, 0. The x squared has a 9 under it, so I'm going to go right 3 and left 3. Put a dot and a dot. The y squared has a 4 under it. We're going up 2, down 2. I connect those up as neat as I can and draw a horizontal ellipse looking like that. The hyperbola, center is still 0, 0. The x squared has a 4 under it, so I go right 2, left 2. The y squared has a 9 under it, agreed, so I'm going to go up 3, down 3, and then make my corner, my corner, my corner, and my corner with an asymptote and an asymptote. And remember the rule, because the x squared is first, this hyperbola opens left and right along the x-axis. So it's going to go that way and that way, getting closer and closer to the asymptotes. Kind of looks like we've got a football here, right? An oval shape with a couple of strings through it. Bottom line is, it certainly looks like there's 4 points of intersection. Right here is going to be one of my answers. Right here they intersect for my second answer. They intersect here in quadrant 2, and they intersect right here in quadrant 3. So quadrants 1, 2, 3, and 4 are my 4 points of intersection. Agreed? How in the world are we going to find that exact spot? Okay? Now, if I looked at this spot in the first quadrant and I said, let's take a guess, where does it look like they intersect? If my picture is even remotely accurate, it certainly looks like they intersect right 2 and then just a little bit past 2 and up probably 1 or a little bit past 1. So if I had to guess, it would be 2 point something, comma, 1 point something. But guessing, of course, isn't good enough. What would we do to figure out where these two conic sections intersect? Well, let's think about it. If I go back to the original problems that were up there, I've got 4x squared plus 9y squared equals 36. I've got 9x squared minus 4y squared equals 36. If you'll remember from Algebra 2, you solved systems of equations using something that was called the elimination technique, remember? If I told you to try to get one of these letters to be eliminated from this problem, let's try to get the y squareds to cancel each other out, because do you agree their signs are already opposites, aren't they? So couldn't we multiply this whole equation by 4, this whole equation by 9, and that would create for me 16x squared plus 36y squared equals, oh boy, 4 times 36 is what? 4 times 30 is 120, 4 times 6 is 24, add them up, we get 144. And then this other one, when I times everything by 9, looks like I get 81x squared minus 36y squared equals 9 times 36. Oh boy, I've got my calculator right here. Let me multiply 9 times 36. And it looks like we get 324. Oh, so I multiplied the first equation by 4 and the second equation by 9 to get the y squareds to turn into opposites, correct? So now when I add these equations together, the y squareds are eliminated from the problem. I use the elimination technique, they're gone, leaving me with 97x squared equals, what's that gonna be, 468. Divide by 97, those would cancel. X squared equals, so I'm going to use my calculator, push 468 divided by 97, giving me 4.8. Actually 4.824, etc. I left that whole decimal on my screen because, of course, we would now square root both sides. Agreed, to get x by itself. And when I square root that number on my screen, 4.824, I get plus or minus, and it looks to me like the answer to the nearest tenth is 2.19, so 2.2. Oh, now that's critical. If I now know my x value is plus or minus 2.2, can't I now take that number and go plug it in, let's say, to the first original equation for the letter x? I'm going to plug it right in there for that x. So in essence, this now says 4 times, now it doesn't matter if it's plus or minus, because when you square it, you're going to get a positive anyway. So if I push 4 times 2.2, I get, whoops, excuse me, we got to take 2.2 and we have to square it, correct? I'm squaring my 2.2 and timesing that by 4 and getting 19.36 plus 9y squared equals 36 minus that over. So 9y squared equals, I'm going to take 36 minus 19.36, giving me 16.64. Divide by 9. So dividing that by 9, you've got what? Y squared equals 1.848 blah, blah, blah. Square rooting both sides, I get plus or minus, and I'm going to go to my calculator, and I'm going to take the square root of that number that's on my screen, and I get, let's see, we've got second square root of 1.848, etc. And it looks like it's plus or minus 1.4. Oh my gosh, we did it. So that tells me, if I look back to the picture we drew, that would be right 2.2 and up 1.4. This point in the fourth quadrant would be right 2.2, but what? Down 1.4. This point would be left and up, so negative 2.2 comma 1.4. And finally, this dot here would be left and down, telling me the ordered pair is negative 2.2, negative 1.4. Wow, obviously that's a little bit detailed. Took me a whole front of a piece of paper to work through one problem. That is a system of conics. Next year in calculus, you could very well be asked to draw that picture. They could say, well, I'll tell you what. If I colored that in right there and said, how much area did I just shade in? What's the area of the shaded region? We're actually figuring out the area from the top of the football to the bottom of the football. And our left and right boundaries are the hyperbola that was intersecting it. So to do that, when you use your calculus skills and techniques and integration techniques, guess what? We need to know the locations of those four intersecting points, because those are the numbers we're going to plug in and crunch when we do our calculus formulas to actually answer a question like that. So it doesn't hurt to certainly be pretty knowledgeable about conics, how to draw them, and try to be creative enough algebraically to see where they intersect. And then finally, guys, last thing today. This is really an extra topic that's thrown in at the end of this chapter. I not necessarily have to test you on it or anything like that. So we're going to do one more little thing on our notes. If you have room on the front, great. I'm going to flip to the back. And I'm going to point out what would you do to attack one like this just to get the ball rolling. And then we're going to stop at that point. You guys have worked hard. I'm going to give you the night off from an assignment. I just wanted to kind of end this chapter by doing a couple of systems of conics to utilize what we've learned in terms of the basic graphing, but yet also somewhat prepare you for calculus for next year. So stay with me. Let's try one more little thing on our notes. Once this is finished, you're done for the day and there's no homework for tomorrow. We would actually start our next unit or our next chapter on Thursday. And then remember, Friday's Good Friday, Easter weekend, there's no school. So our last session this week will be tomorrow on Thursday, April 9th. Okay, if you take a look at this one, we've got a what and a what. If you were doing this on your own, I hope you'd say, there's only one letter squared on this problem. That makes this a parabola. There's two letters squared here, and the coefficients are the same, making this what? A circle. And on a circle, remember, we don't want those coefficients there. I would divide both sides by 4, giving me x plus 2 squared plus y squared equals 16. Agreed? So I've got a parabola and a circle. If I graph the circle, now careful, it says x plus 2. So you agree the center would be what? Negative 2 comma 0. I'm going to go left 2 and up 0. 16 is the number at the end. So since that's always, remember, my radius squared, my radius must be 4. So I'm going to go right 4, left 4, up 4, and down 4. And I draw a nice neat circle centered at -2, 0. Okay? The parabola, let's think back to yesterday, all right? Y squared. If it's the y that's squared, that means it opens either what, left or right? This is a +8. It's a parabola pointing to the right, whose vertex, of course, is 0, 0. And if I take 4p and set it equal to the number 8, it's pretty obvious p would be 2. So if I go to graph that, the vertex is 0, 0. My focus is 2 units to the right of the vertex, just like yesterday. So I go right 2, and that would be my focus. The segment that you're imagining through that focus is a total of 8. So I'm going to go up 4, down 4, draw my parabola, and back to the original question. Oh, where do they intersect? Where do these two conic sections intersect? It looks like they intersect twice. Agreed? The parabola comes up and it intersects the circle right there. And then they intersect right there. Once in quadrant 1 and once in quadrant 4. So the question is, and we're not going to go through the whole algebraic process, but what would we do to solve this system algebraically and try to calculate the points of intersection? Well, we can't use the we can't use the elimination technique, because think about it. This said y squared equals 8x. This says 4 parentheses x plus 2 squared plus 4y squared equals 64. Now remember, we did simplify that into x plus 2 squared plus y squared equals 16. So we'll work with that version of our circle. We can't take the parabola, pick it up, and lay it underneath this equation and try to get one of our letters to cancel. Oh, because this has an x squared and a y squared, and the parabola only has one letter squared. So you can't line up the system and try the elimination technique. So what would we do? Well, be creative algebraically. Look at this, guys. Doesn't it say that y squared is equal to 8x? So can't you take this 8x, since it's equal to y squared, and go plug it in for that y squared? So this ends up being, when I square this, remember we get x squared plus, what would that be? 4x plus 4 plus, now it says y squared, but y squared equals 8x. So I put 8x in his place equals 16. And oh my gosh, I end up with a quadratic equation of x squared plus, let's combine like terms, 12x. Of course, I would subtract over the 16, right? Because we're trying to get it equal to 0 because it's a quadratic equation. So if that's a 4 and I subtract over a 16, I've got minus 12 equals 0. Now, that does not factor, and because it doesn't factor, you'd have to use the quadratic formula. I did do that. We ended up getting x equals 0.9 for our answer. And so if that 0.9 makes sense, because look up at your picture, we're going to go right 0.9 and up a certain height. 0.9 is that x-coordinate. Negative 0.9, positive 0.9 is also this guy's x-coordinate. His y is going up, his is going down. So we'll have a positive y and a negative y. And we could actually finish the problem, I guess, now by simply doing what? Taking that 0.9, plugging it in for that x right there. 8 times 0.9 would be 7.2 equals y squared. So if I square rooted 7.2 on my calculator, I guess we did get this one done. we end up with, looks like 2.7. So this would be up 2.7, which certainly looks correct. This point would be down at negative 2.7. And we were able to calculate the two places where the circle and the parabola actually intersected. Okay? So that's a great way to end our conic section unit. You did a super job. Thank you very much. Hope that makes sense. You certainly could find some of those online if you wanted to try a problem or two on your own. That wraps up our chapter. We'll start a new unit tomorrow. I'll see you then.